Good evening, dear listener, and welcome back to the Sleepy Scholar. I'm so glad you've chosen to spend this quiet hour with us tonight. Perhaps you're settling into your favorite pillow or watching the last light fade beyond your window. Whatever brings you here, know that this is a place for calm curiosity, for gentle wonder, and for the kind of stories that invite both mind and spirit to rest. Tonight, we turn our attention to a figure whose name has become synonymous with genius itself. And yet, beneath the mythology and the wild-haired photographs, there lived a man of profound simplicity, a dreamer who spoke late as a child but thought deeply all his life. A quiet scholar who sat at a patent office desk and reimagined the very fabric of time and space. Have you ever wondered what dreams danced in the mind of the man who reimagined time itself? Picture, if you will, a small room lit by a single oil lamp. Papers scattered across a wooden desk, some covered in equations, others bearing only a few lines. Fragments of thought captured before they could drift away. The scent of ink and old books mingles with the cool night air drifting through an open window. And there, in the stillness, sits a young man with a violin resting against the wall beside him, his eyes distant, his mind tracing invisible lines through the cosmos. This is where genius lived, not in grand laboratories or marble halls, but in quiet moments of reflection, in the space between question and answer, in the gentle hum of curiosity that refused to be silenced. Tonight, we explore the life of Albert Einstein, not merely the scientist who rewrote physics, but the human being who loved music, who felt out of place in rigid classrooms, who doubted himself even as he unveiled the universe's deepest secrets. We'll walk through his early years, trace his journey of discovery, stand beside him in his moments of breakthrough, and understand the personal struggles that shaped his extraordinary path. Before we begin this journey together, if you're finding comfort in these stories, if this gentle exploration helps you unwind after a long day, consider subscribing to the Sleepy Scholar. A simple like or a quiet comment about what brings you peace. These small gestures help us continue crafting these bedtime journeys for curious souls like yours. There's no pressure, only an invitation to become part of this thoughtful community. Now, let us return to that lamplit room, to that quiet mind gazing at the stars, and ask ourselves, what shaped the consciousness that would one day teach humanity to see time not as a river flowing in one direction, but as a gentle fabric, woven with space itself, bendable and beautiful? Let's begin at the beginning. In a small German city where a child was born who would change everything, though no one, least of all his worried parents, could have known it then. The child who thought in silence. On March 14, 1879, in the medieval city of Ulm, nestled along the banks of the Danube River in southern Germany, Pauline and Hermann Einstein welcomed their first child into the world. The city's narrow cobblestone streets had witnessed centuries of history, its Gothic cathedral reaching toward the heavens, as if asking the eternal questions that their son would one day attempt to answer. They named him Albert. From the beginning, young Albert was different. He spoke late, so late that his parents consulted doctors, their worry growing with each silent month. While other children chattered and played with easy facility, Albert remained in a world of his own, observing, thinking, processing the world in ways that didn't require words. But silence, as we often forget, is not absence. Sometimes silence is the deepest form of listening. When Albert finally did speak, around the age of 4 or 5, he did so in full sentences, carefully constructed, each word chosen with deliberate thought. He had been listening all along, building entire architectures of understanding before bothering to express them aloud. This pattern of deep internal contemplation before external expression would characterize his entire approach to science. Imagine the young boy, perhaps 3 or 4 years old, sitting on the floor of his family's modest apartment in Munich, where they had moved shortly after his birth. His father, Hermann, was an engineer and businessman who ran an electrical engineering company with Albert's uncle. The apartment often hummed with talk of dynamos and electrical currents, of invisible forces that could light lamps and power machinery. One day, when Albert was around 5 years old and ill in bed, his father brought him a gift, a simple pocket compass. This moment, which Einstein would remember vividly throughout his entire life, became one of those quiet pivots upon which destiny turns. The boy stared at the compass needle. No matter how he turned the case, the needle swung back, always pointing north. Always. His small hands rotated it again and again, his young mind grappling with a profound mystery. Something invisible was acting on the needle. Some force, unseen and untouchable, reached across empty space and commanded the needle's direction. I can still remember, Einstein would write decades later, that this experience made a deep and lasting impression upon me. Something deeply hidden had to be behind things. Think about that for a moment. While we might take such a phenomenon for granted, to a 5-year-old child lying in bed, this was nothing short of magic, but a magic that demanded explanation. The universe, young Albert suddenly understood, was filled with invisible forces, with hidden structures, with mysteries that whispered just beyond the edge of perception. This wasn't merely a child's idle curiosity. This was the awakening of a particular kind of mind, one that would never be satisfied with surface explanations, one that would always ask, but what lies beneath? What secret architecture supports the world we see? His mother, Pauline, brought a different kind of invisible force into his life: music. She was an accomplished pianist, and their home was often filled with the mathematical beauty of Mozart and Bach, the gentle cascades of melody that seemed to follow rules as precise as any physics equation, yet somehow spoke directly to the soul. When Albert was 6, his mother insisted he take violin lessons. At first, the young boy resisted. The rigid structure of practice scales and exercises felt oppressive, another system imposed from outside. But then, around age 13, he discovered the violin sonatas of Mozart. Suddenly, the violin wasn't an instrument of discipline but of expression, a way to give voice to the harmonies he felt within. Throughout his life, Einstein would turn to music when his scientific work reached an impasse. He would play his violin, which he affectionately named Lena, working through complex problems not with equations but with melody, seeking in Bach's mathematical fugues the patterns that might unlock the universe's secrets. "If I were not a physicist," he would later say, "I would probably be a musician. I often think in music. I live my daydreams in music." I see my life in terms of music. Here was a boy learning that the universe spoke in multiple languages: mathematics, music, the mysterious pull of invisible forces, and that all of these languages were somehow describing the same underlying reality. But his path through formal education would be anything but smooth. The student who couldn't conform. Young Albert attended Catholic elementary school in Munich, and from the earliest days, he chafed against its rigid structure. The German educational system of the 1880s prized obedience, rote memorization, and military-style discipline. Students stood when teachers entered, recited lessons in unison, and absorbed knowledge without question. For a mind like Einstein's, questioning, independent, fascinated by ideas rather than facts, this environment felt like a cage. Picture the classroom. Rows of stiff-backed wooden desks, children sitting with perfect posture. A stern teacher at the front demanding exact recitation of historical dates or grammatical rules. And there, in the middle rows, a boy whose attention drifts toward the window, where light streams in and dust motes dance in invisible currents of air, following paths determined by forces he cannot yet name. He was not a rebellious child, not outwardly defiant, but he was profoundly disengaged from education as performance, education as obedience. His teachers found him stubborn, insolent even, because he asked why when they expected silent acceptance. He challenged assumptions not from arrogance but from genuine need to understand the foundations beneath the facts. One teacher famously told him he would never amount to anything. Another suggested he leave school because his mere presence disrupted the classroom, not through misbehavior, but through his persistent questioning, his refusal to accept statements on authority alone. Yet in private, young Albert was teaching himself. By age 12, he had discovered a geometry textbook. He would later call it his holy geometry book, and devoured it with passion that his regular schoolwork never inspired. The elegant proofs, the way complex truths could be derived from simple axioms, the pure logical beauty of mathematics. This was education that spoke to his soul. That same year, 1891, a young medical student named Max Talmud began joining the Einstein family for weekly dinners, a Jewish tradition of hosting a less fortunate student for a meal and conversation. Max brought books, popular science texts, philosophical works, mathematical treatises. He and young Albert would discuss Kant and geometry, the nature of light and the structure of space, far into the evening. Through Max, Einstein encountered People's Books on Natural Science by Aaron Bernstein, which described riding alongside electricity through a telegraph wire. This image captivated Albert's imagination. What would it be like to travel alongside a beam of light? Would you see the light wave frozen in space? Or would something stranger occur? This thought experiment, imagining himself riding a light beam, would germinate in Einstein's mind for years, eventually blossoming into the special theory of relativity. But we're getting ahead of ourselves. For now, he was simply a curious boy, lying in bed before sleep, imagining impossible journeys through the cosmos. When Albert was 15, his father's business failed. The family moved to Italy, to Milan, and later to Pavia, seeking better opportunities. But Albert was left behind in Munich to finish his schooling at the Luitpold Gymnasium. Imagine the boy's loneliness. His family across the Alps, his educational environment stifling, his future uncertain. He endured it for a few months, but the separation and the oppressive school environment became unbearable. Using a doctor's note claiming nervous exhaustion, not entirely false, he left the gymnasium without graduating and made his way to Italy to reunite with his family. Picture his relief as the train carried him south, over mountain passes, into the sunlit warmth of northern Italy, away from rigid classrooms and toward the family he loved, toward a landscape of art and creativity and less rigid thinking. In Italy, Einstein spent a blissful year helping with his father's business, hiking through the Italian countryside and continuing his self-education. He even wrote his first scientific paper at age 16, a thought experiment about investigating the state of the ether through magnetic fields. Though the paper was naive and never published, it showed a mind already grappling with the fundamental questions that would define his career. But he needed formal credentials. In 1895, at age 16, he took the entrance exam to the Swiss Federal Polytechnic in Zurich, an institution that didn't require a high school diploma. He failed. His mathematics and physics scores were excellent, but his performance in languages, biology, and literature fell short. Rather than despair, Einstein spent a year at a progressive secondary school in Aarau, Switzerland. This school was a revelation. Unlike the authoritarian German system, the Aarau school encouraged independent thought, scientific inquiry, and student initiative. Teachers treated students as intellectual partners rather than empty vessels to be filled. Here, Einstein flourished. He lodged with the family of Jost Winteller, a teacher at the school, and fell in love, both with physics and with Jost's daughter, Marie. He spent afternoons discussing science, taking long walks through the Swiss countryside, thinking about light and motion and the nature of electromagnetic waves. In later years, Einstein would describe this time as formative. The Swiss emphasis on democracy, independent thinking, and practical education suited him perfectly. Switzerland would become his adopted homeland, the place where his mind found room to breathe. In 1896, he successfully entered the Zurich Polytechnic, the institution now known as ETH Zurich, where he would study to become a physics and mathematics teacher. As we watch young Einstein walk through the doors of the Polytechnic that autumn day, perhaps we can pause and feel the gentle turning of fate. How many students had passed through those same doors? How many would be forgotten? What made this particular mind different? Perhaps it was the way he questioned everything. Perhaps it was his ability to visualize abstract concepts, to imagine himself riding alongside light beams or falling freely through space. Perhaps it was his stubborn refusal to accept answers that didn't satisfy his deep need for foundational understanding. Or perhaps, and this is the most beautiful possibility, genius is simply the meeting of exceptional ability with unstoppable curiosity, nurtured by just enough freedom to follow its own strange path. Let us walk with him now into those university years, where the foundations of revolution were quietly being laid. The university years, freedom and frustration. The Zurich Polytechnic should have been Einstein's paradise. Here was a serious scientific institution, filled with laboratories and libraries, professors conducting cutting-edge research, fellow students passionate about physics and mathematics. Here, finally, was the intellectual community he'd been seeking. And yet, Einstein's relationship with formal higher education remained complicated. He attended lectures irregularly, preferring to study theoretical physics on his own, reading the latest papers by Boltzmann, Maxwell, Kirchhoff, and Hertz. His professors, particularly Heinrich Friedrich Weber, who taught physics, found him frustrating. Einstein was brilliant but unconventional, more interested in foundational questions than in experimental technique, more likely to be found in a coffee shop discussing philosophy than in a laboratory measuring electromagnetic phenomena. Picture the university coffee houses of Zurich at the turn of the century. Dim rooms thick with pipe smoke and intellectual fervor, students hunched over tables covered with papers and empty coffee cups, debating the nature of atoms, the reality of ether, the meaning of Maxwell's equations. This was Einstein's true classroom. It was here, in these informal gatherings, that Einstein met the people who would shape his personal and intellectual life. Michel Bessot became his closest friend, a brilliant engineer with whom Einstein would discuss physics for hours, using Bessot as a sounding board for his wildest ideas. Decades later, Einstein would acknowledge Bessot in his 1905 relativity paper as the person who helped him clarify his thoughts. And here too Einstein met Mileva Maric, the only woman in his physics program, a serious and talented student from Serbia who shared his passion for theoretical physics. Their relationship began as an intellectual partnership, studying together, discussing the latest developments in physics, challenging each other's understanding. They fell in love. Their relationship would be complex and ultimately unhappy, but in these early years, they were intellectual companions, two outsiders in the academic world supporting each other's ambitions. Letters between them revealed discussions of scientific problems, shared dreams of solving the mysteries of molecular forces and electromagnetic theory. But Einstein's rebellious streak continued to cause problems. He frequently skipped classes, relying on his friend Marcel Grossman's meticulous lecture notes to prepare for exams. He pursued his own reading rather than following the prescribed curriculum. He alienated Professor Weber by pointing out errors and by his obvious lack of interest in experimental work. Still, his mathematical gifts were undeniable. When examination time came, Einstein could synthesize material quickly, his powerful intuition allowing him to grasp the essential patterns that eluded more conventional students. In 1900, Einstein graduated from the Polytechnic with a diploma allowing him to teach mathematics and physics. He was 21 years old, intellectually confident, ready to contribute to the scientific community. What followed was not triumph but 3 years of frustration and rejection. The wilderness years, patent office clerk. Einstein desperately wanted an academic position, an assistantship that would allow him to continue research while earning a living. He applied to professor after professor at universities across Europe. Each application was rejected or ignored. Professor Weber, who might have helped him, declined to offer a position, likely alienated by Einstein's rebellious attitude during his studies. Picture Einstein during these years, a young man whose confidence in his own intellectual abilities had been tempered by the harsh reality that the academic world had no place for him. He took temporary teaching positions, tutoring students, living hand-to-mouth, borrowing money from friends. His relationship with Mileva deepened. In 1901, she became pregnant, a scandal in that era. She returned to her family in Serbia and, in 1902, gave birth to a daughter, Liesl. What happened to this child remains one of the mysteries of Einstein's life. She may have died in infancy or been given up for adoption. Einstein never spoke of her publicly, and after a few mentions in private letters, she disappears from the historical record. A ghost at the margins of genius, a reminder that even brilliant minds exist in messy, complicated human lives. Einstein's fortunes changed through friendship. Marcel Grossman, his university friend whose notes had helped Einstein pass his exams, mentioned Einstein's situation to his father, who had connections at the Swiss Patent Office in Bern. A position was available for a patent examiner, third class, a government clerk who would review technical patent applications and evaluate their novelty and feasibility. It wasn't academic glory, but it was stable employment. In 1902, Einstein accepted the position and moved to Bern. Imagine him settling into that city, a beautiful medieval town where arcaded streets provided shade in summer and shelter in winter, where the river Ara flowed green and cold from mountain glaciers, where the old clock tower marked the hours with mechanical precision. He found an apartment, modest but his own, and began his work at the patent office. The job was, in many ways, perfect for Einstein. It required only about 6 hours of concentrated work per day, evaluating inventions related to electrical devices, mechanical instruments, and telecommunications equipment. Einstein's task was to understand the essential idea behind each invention, to see through the specific implementation to the underlying physical principle. This work trained his mind in a particular way, to extract the essential from the incidental, to understand what was truly necessary to an idea and what was merely decorative detail. Years later, Einstein would credit the patent office with teaching him to think clearly about physical concepts. But more importantly, the position left his mind free. After completing his patent evaluations, Einstein would pull papers from his desk drawer and work on theoretical physics, pursuing questions that had no immediate practical application, no supervisor demanding results, no pressure to publish in prestigious journals or impress senior professors. He was free to follow his curiosity wherever it led. In 1903, Einstein and Mileva married in a quiet ceremony. In 1904, their son Hans Albert was born. Einstein was now a family man, a government clerk with a small apartment in Bern, earning a modest salary, unknown to the scientific community. To all outward appearances, he had settled into obscurity. But in that quiet apartment, in his spare time, in the hours stolen from sleep and leisure, Einstein was thinking about light. The miracle year, 1905. Picture the patent office in Bern, early in the new century. A room with large windows letting in clear Swiss light, desks arranged in neat rows, the scratch of pens on paper, the rustle of patent applications. And at one desk, a young man with unruly dark hair, perhaps 25 or 26 years old, working efficiently through the technical drawings and descriptions before him, but with a certain distraction in his eyes, as if part of his mind were always elsewhere. Riding alongside beams of light, watching molecules dance in liquids, contemplating the nature of time itself. The year 1905 has become legendary in the history of science. Einstein's miracle year, or annus mirabilis, when a patent clerk third class published 4 papers in the prestigious journal Annalender Physik, each of which would have been sufficient to establish a major scientific reputation and together revolutionized physics. Let us slow down and feel the magnitude of what occurred. These weren't incremental advances or minor corrections to existing theory. These were fundamental reconceptualizations of reality itself. The photoelectric effect. The first paper, published in March 1905, addressed a phenomenon that had been puzzling physicists: the photoelectric effect. When light strikes certain metal surfaces, it knocks electrons free, but the number of electrons released depends not on the intensity of the light but on its frequency. Brighter light produces more electrons, but only if the light's color, frequency, is above a certain threshold. Classical physics, the wave theory of light that had dominated the 19th century, couldn't explain this. If light were simply waves, then brighter light, regardless of color, should provide enough energy to free electrons. Einstein proposed something radical. Perhaps light, despite behaving as waves in many experiments, also exists as discrete particles, quantum packets of energy, later called photons. The energy of each photon depends on the light's frequency. An electron can only be ejected if struck by a photon carrying sufficient energy, which explains why low-frequency red light, no matter how bright, can't free electrons if high-frequency blue light is required. Imagine sitting with Einstein as he worked through this idea. He wasn't performing experiments. He was thinking deeply about the meaning of existing experimental results, finding patterns others had missed, daring to propose that light had a dual nature, sometimes wave, sometimes particle. This paper would eventually earn Einstein the Nobel Prize in 1921. Notably, not for relativity, which remained controversial, but for this more practical contribution to quantum theory. But in 1905, most physicists found the idea too strange to accept. Light as particles? When wave theory had been so successful, Einstein himself recognized the strangeness. But he followed where the evidence led, willing to embrace paradox if that's what nature demanded. Brownian motion. The second paper, published in May, addressed an even more fundamental question. Do atoms really exist? Today, atomic theory is so thoroughly accepted that this question sounds absurd. But in 1905, atoms were still theoretical entities, useful for calculations but not necessarily real. Some prominent scientists, including the chemist Wilhelm Ostwald and the physicist Ernst Mach, argued that atoms were merely convenient fictions, calculational devices with no physical reality. Einstein provided proof of their reality through an analysis of Brownian motion, the random, jittery movement of tiny particles suspended in liquid, first observed in pollen grains by the botanist Robert Brown in 1827. Einstein showed that this motion could be explained by countless collisions with water molecules. Atoms and molecules too small to see directly but whose reality could be inferred from their cumulative statistical effect. He worked out the mathematical relationship between the particle's motion, the temperature of the liquid, and the size of the hypothetical molecules. His predictions were soon confirmed experimentally by the French physicist Jean Perrin. providing some of the most convincing evidence for atomic theory and effectively ending the debate about atoms' existence. Picture Einstein's satisfaction. He had touched the invisible, made the theoretical tangible, shown that careful reasoning about statistical effects could reveal hidden structures of reality. Special relativity. The third and most famous paper appeared in June. It was titled modestly, "On the Electrodynamics of Moving Bodies." It contained no citations, no footnotes, no references to previous work, just pure reasoning from first principles. This paper introduced what we now call special relativity. To understand what Einstein accomplished, we must first understand the problem he was trying to solve. For decades, physicists had been troubled by an apparent contradiction between two pillars of physics: Newton's laws of motion and Maxwell's equations of electromagnetism. Newton's laws were relative. They worked the same way regardless of whether you were standing still or moving at constant velocity. If you drop a ball on a moving train, it falls straight down from your perspective, just as if you were standing on stationary ground. There's no experiment you can perform inside the train without looking outside that will tell you whether you're moving or at rest. But Maxwell's equations predicted that light travels at a fixed speed, roughly 300,000 kilometers per second. And here was the puzzle. Speed relative to what? If light has a fixed speed, shouldn't there be some absolute reference frame, some cosmic background against which all motion is measured? Physicists had hypothesized the existence of the luminiferous ether, an invisible substance filling all space, through which light waves propagated the way sound waves move through air. Elaborate experiments, particularly the famous Michelson-Morley experiment of 1887, tried to detect Earth's motion through this ether by measuring tiny differences in the speed of light in different directions. They found nothing. Light's speed appeared constant regardless of Earth's motion. Most physicists responded by making the ether theory more complicated. Perhaps Earth dragged ether along with it, or perhaps objects contracted when moving through ether in ways that happened to hide the expected effects. Einstein took a different approach. He asked, what if the null result isn't a failure to detect the ether, but reveals something profound about nature itself? What if there is no ether? What if light speed is truly constant for all observers, regardless of their motion? This simple acceptance of what the experiments actually showed led Einstein to reconceptualize space and time themselves. Let's slow down and feel what this means. Imagine you're on that train again, moving smoothly at high speed. You shine a flashlight forward. Intuitively, you might think the light should move at the speed of light plus the train's speed. But Einstein's theory says no. An observer watching from the platform would also measure your light as moving at exactly the speed of light, the same speed you measure. How is this possible? How can two observers in relative motion both measure the same light beam as traveling at the same speed? The answer requires rethinking time itself. Time, Einstein realized, is not absolute. Two events that are simultaneous for one observer may not be simultaneous for another observer in motion relative to the first. Time literally runs at different rates for observers in relative motion. Space contracts along the direction of motion. A meter stick moving relative to you is actually shorter than an identical meter stick at rest. These aren't optical illusions or measurement problems. They're fundamental features of reality. Space and time are not separate, absolute entities but are interwoven into a four-dimensional fabric. Space-time. Picture Einstein working through these ideas, perhaps late at night in his apartment, Mileva asleep, baby Hans Albert in his cradle, the city of Bern quiet beyond the windows. On paper before him, the equations that would reshape human understanding of reality. No laboratory equipment, no expensive instruments, just thought, careful reasoning about the meaning of simultaneity and the constancy of light speed. He had been thinking about these problems for years, since he was 16 and first imagined riding alongside a light beam. What would you see? Would the electromagnetic wave appear frozen, stationary beside you? But Maxwell's equations didn't allow for stationary electromagnetic waves. They always moved at light speed. The contradiction troubled him for a decade. The breakthrough came, Einstein later recalled, during a conversation with his friend Michel Besso. They walked together, discussing the problem of synchronizing clocks. How do you ensure two separated clocks show the same time? The obvious method is to send a light signal between them. But if light takes time to travel, and if different observers are in motion, suddenly Einstein saw it. The concept of simultaneous events depended on your frame of reference. There was no absolute simultaneity, no cosmic clock ticking the same time everywhere. Time itself was relative. Einstein later described this as the happiest thought of his life. Equals mc squared. The fourth paper, published in September 1905, was brief, only 3 pages, but contained perhaps the most famous equation in physics. This paper was actually a follow-up to the relativity paper, exploring a consequence Einstein had noticed. If energy and mass are both manifestations of the same underlying reality, related by the speed of light squared, equals mc squared. Energy equals mass times the speed of light squared. Let's pause and contemplate this equation's simplicity and profundity. It tells us that mass and energy are interchangeable, two forms of the same thing. A small amount of mass corresponds to an enormous amount of energy because the speed of light is such a large number, and you square it. This equation would later explain the power source of stars, including our sun. It would enable both wonderful and terrible nuclear medicine and nuclear weapons. It suggested that the universe was far stranger and more unified than anyone had imagined. And Einstein derived it with pure thought, sitting at a patent office desk in Switzerland. After the miracle, slow recognition, you might imagine that these papers immediately catapulted Einstein to scientific fame. They didn't. The initial reaction was muted. A few physicists noticed. Max Planck, one of the founders of quantum theory, found Einstein's work brilliant and began corresponding with him. But most of the scientific establishment either ignored the papers or found them too strange to take seriously. Einstein remained at the patent office. He was promoted to technical expert second class in 1906, a modest advancement. He continued his research in his spare time, developing his ideas further, beginning to think about gravity and how it might fit into the relativistic framework. Picture him during these years, a young father walking his son to school, an efficient patent clerk evaluating devices for measuring electric current or synchronizing clocks. How fitting, given his work on relativity. And a revolutionary physicist whose ideas were slowly, very slowly, beginning to seep into the consciousness of the scientific community. In 1908, Einstein finally received an academic appointment, a part-time position at the University of Bern, where he lectured while still working at the patent office. His lectures were unconventional, interactive, more like conversations than formal presentations. Sometimes only a handful of students attended, but gradually word spread. Here was a genuine original thinker, someone asking questions others hadn't thought to ask, someone willing to overturn centuries of assumptions if logic demanded it. In 1909, Einstein received his first full-time academic position at the University of Zurich. He left the patent office after 7 years, those quiet years that had been, in their way, the most productive of his life. Imagine his mixed feelings. The patent office had been a sanctuary, a place where he was free from academic politics and pressure, free to think without constraints. Academia offered resources and recognition, but also demands, bureaucracy, the need to navigate departmental disputes and satisfy administrators. He was 30 years old, no longer unknown but not yet the Einstein of legend. That would come later, after his greatest work was complete. For Einstein was thinking about gravity, working toward a theory that would make special relativity look simple by comparison. The happiest thought, falling freely. In 1907, while still at the patent office, Einstein had another crucial insight, what he would later call the happiest thought of my life. He imagined a person falling freely from a roof. Strange thing to be happy about, perhaps, but imagine it from the faller's perspective. During the fall, before hitting the ground, the person feels weightless. If they drop something, it falls alongside them. From their perspective, in that moment of free fall, gravity has disappeared. Einstein realized this was more than a curiosity. It revealed something fundamental about gravity's nature. In Newton's theory, gravity was a force pulling objects together. But Einstein saw that gravity could also be understood as the absence of force. A person standing on Earth's surface feels their weight. They feel force because the ground prevents them from falling. The natural state, the state without force, is free fall. This led Einstein to what he called the equivalence principle. You cannot distinguish between gravitational effects and the effects of acceleration. An astronaut in a rocket accelerating through empty space at exactly 9.8 meters per second squared would feel exactly the same sensation as standing on Earth's surface. Picture Einstein pacing his apartment, excited, trying to explain this idea to Mileva. Gravity and acceleration are equivalent, indistinguishable. This meant that gravity wasn't really a force at all, not in the Newtonian sense. It was something else, something geometric, something to do with the structure of space and time themselves. But working out the mathematics would take 8 years of intense effort, some of the most difficult years of Einstein's life. The struggle toward general relativity. By 1911, Einstein had moved to Prague, accepting a professorship at the German university there. The city was beautiful but politically tense, the Austro-Hungarian Empire showing the strains that would soon tear it apart in World War I. Einstein found the rigid academic hierarchy and ethnic tensions uncomfortable. But he was thinking about gravity constantly. He realized that light, having energy, must be affected by gravitational fields. Light passing near a massive object like the sun should be deflected, bent from its straight path. a prediction utterly foreign to Newtonian physics, where light, having no mass, shouldn't interact with gravity at all. He calculated that starlight grazing the sun's surface should be deflected by a tiny but measurable angle. If this could be observed during a solar eclipse, when stars near the sun become visible, it would provide a test of his emerging theory. The mathematics, however, was daunting. Special relativity had used relatively simple mathematics, algebra, and basic calculus that any physics student could follow. But to describe gravity as the curvature of spacetime itself required advanced mathematics Einstein hadn't studied. Tensor calculus, differential geometry, the mathematics of curved spaces. In 1912, Einstein returned to Zurich, accepting a position at ETH, his alma mater. And here, fortune blessed him again through friendship. Marcel Grossmann, the same friend whose lecture notes had helped Einstein graduate, whose father had helped him get the patent office job, was now a professor of mathematics at ETH. Einstein appealed to him. "Grossmann, you must help me or I'll go crazy." Grossmann introduced Einstein to the mathematics of curved spaces, developed decades earlier by Bernhard Riemann and others for purely abstract reasons, with no thought that it might describe physical reality. These mathematical tools allowed Einstein to express his physical intuitions precisely. Picture them working together. Einstein with his powerful physical intuition, his ability to visualize how things must work, and Grossmann with his mathematical sophistication, able to translate Einstein's visions into rigorous equations. By 1913, they published a preliminary version of the theory, but Einstein wasn't satisfied. Something wasn't quite right. The equations didn't have the mathematical elegance he expected, didn't satisfy certain principles of symmetry that he felt they should. He struggled for 2 more years, trying different approaches, making mistakes, publishing preliminary versions only to retract them. His marriage to Mileva was deteriorating under the strain of his obsessive work, his frequent absences, his emotional distance. In 1914, he accepted a prestigious position in Berlin, a research position at the Prussian Academy of Sciences with no teaching duties, just time to think and calculate. Mileva refused to accompany him. She returned to Zurich with their 2 sons, Hans Albert and Eduard, born in 1910. The marriage was effectively over, though they wouldn't divorce until 1919. Einstein threw himself into his work. World War I had begun. The nationalist fervor sweeping Europe appalled him. Scientists he respected signing manifestos supporting their nation's war efforts, rationality swept aside by tribal loyalty. Einstein, a lifelong pacifist, felt increasingly alienated from the militaristic culture surrounding him. But in his study, far from the battlefields, he was completing his greatest work. The beauty of curvature, general relativity. In November 1915, in a series of 4 lectures to the Prussian Academy, Einstein presented the final, complete form of general relativity. The theory's central idea is breathtaking in its elegance. Gravity is not a force but the curvature of spacetime caused by the presence of mass and energy. Imagine it this way. Picture spacetime as a vast, flexible fabric, something like a rubber sheet stretched smooth and flat. Now place a heavy ball on the sheet. The fabric dimples around the ball, creating a curved depression. If you roll a smaller ball nearby, it doesn't travel in a straight line but curves toward the depression. not because the large ball is pulling it, but because the very fabric of the sheet is curved. This is what mass does to space-time. The sun doesn't pull Earth with an invisible force. Rather, the sun's mass curves the space-time around it, and Earth simply follows the straightest possible path, what mathematicians call a geodesic, through this curved geometry. Earth orbits because it's moving through curved space-time, following the contours the sun has created. The mathematics expressing this idea is contained in Einstein's field equations. 10 interrelated equations, actually components of a single tensor equation, of extraordinary complexity and beauty. On one side of the equation is the curvature of space-time. On the other side is the distribution of mass and energy. Mass and energy tell space-time how to curve. The curvature of space-time tells mass and energy how to move. The physicist John Archibald Wheeler would later summarize it poetically. Matter tells space how to curve. Space tells matter how to move. Think about the intellectual journey that led here, from a boy wondering at a compass needle, through years of questioning rigid assumptions, through the recognition that time itself is relative, to this final insight that gravity, the force that holds planets in their orbits and makes apples fall, isn't a force at all but the shape of reality itself. Einstein completed the equations in a state of exhaustion and exhilaration. He wrote to his friend Paul Ehrenfest, "The theory is of incomparable beauty, but only one colleague has really understood it." For several weeks after completing the theory, Einstein suffered heart palpitations, couldn't work, felt physically drained by the intensity of the effort. He had pushed himself to the absolute limit of his capabilities. But he had succeeded. And now came the question, was it true? Testing reality. The eclipse of 1919. General relativity made specific predictions that differed from Newtonian gravity. Most of these differences were tiny, detectable only in extreme situations, but a few could be tested with existing technology. Einstein's theory predicted 3 key observable effects. First, it explained a long-standing mystery: the peculiar orbit of Mercury. Mercury, the closest planet to the Sun, doesn't orbit in a perfect, closed ellipse as Newton's theory predicts. Instead, its orbit slowly rotates. The axis of its ellipse gradually shifts, a phenomenon called perihelion precession. Astronomers had known about this anomaly for decades and had invented various explanations, including a hypothetical planet closer to the Sun they called Vulcan. General relativity explained Mercury's orbit perfectly, without requiring any new planets or ad hoc adjustments. The Sun's intense gravitational field, its strong curvature of spacetime, was sufficient to account for the observed motion. When Einstein first calculated this and saw his equations reproduce Mercury's orbit exactly, he later recalled, "I was beside myself with joyous excitement. For a few days, I was beside myself with ecstasy." Second, the theory predicted that clocks in stronger gravitational fields run slower, what's called gravitational time dilation. This effect was too small to measure with 1915 technology but would be confirmed decades later and is now routinely accounted for in GPS satellites. Third, and most dramatically, light passing near a massive object should be deflected by an amount twice as large as the simplified calculation Einstein had made years earlier. Starlight passing just by the sun's edge should be deflected by about 1.75 arcseconds. A tiny angle, but potentially measurable. The problem: stars near the sun are only visible during a total solar eclipse. World War I prevented any eclipse expeditions. But in 1919, shortly after the war's end, the British astronomer Arthur Eddington organized 2 expeditions to observe the solar eclipse of May 29th, one to Sobral, Brazil, and one to the island of Principe off the coast of West Africa. Picture Eddington, a Quaker and pacifist like Einstein, determined to test a German scientist's theory in the aftermath of a war that had torn Europe apart. Science, Eddington believed, transcended national boundaries. Truth didn't care about which side you'd fought on. The expeditions were fraught with difficulty. Clouds threatened to obscure the eclipse. The photographic plates had to be prepared perfectly. The measurements required comparing star positions during the eclipse with their positions 6 months later, when those same stars would be visible at night. On November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London, Eddington announced the results. The light deflection observed matched Einstein's prediction. Newton's theory was insufficient. Einstein's general relativity appeared correct. The philosopher Alfred North Whitehead, who attended the meeting, later described the scene. The whole atmosphere of tense interest was exactly that of the Greek drama. We were the chorus commenting on the decree of destiny as disclosed in the development of a supreme incident. The London Times ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Overnight, Einstein became a global celebrity, perhaps the first scientific celebrity of the modern age, his face recognized worldwide, his name synonymous with genius itself. The weight of fame. Imagine Einstein waking up in Berlin on November 7, 1919, to find himself suddenly world famous. Reporters camping outside his modest apartment. Telegrams arriving from around the globe. Strangers stopping him on the street. Photographers demanding he pose while sticking out his tongue, which he eventually did in 1951, creating one of the most iconic photographs of the 20th century. For a man who valued solitude and contemplation, who had spent years in quiet obscurity happily working on abstract problems, this sudden fame was disorienting and, in many ways, unwelcome. Yet Einstein handled celebrity with remarkable grace and humor. He was asked to explain relativity to laypeople countless times. He developed a gift for metaphor and analogy. Put your hand on a hot stove for a minute, and it seems like an hour, he once said. Sit with a pretty girl for an hour, and it seems like a minute. That's relativity. He gave lectures worldwide, traveling to America, Japan, Palestine, throughout Europe. Everywhere he went, massive crowds gathered. In Japan, thousands waited at train stations hoping to glimpse him passing through. In America, he was received like a head of state. But this fame had a dark side. Einstein was Jewish, and in the chaotic, resentful atmosphere of post-war Germany, anti-Semitism was rising. Some German physicists, bitter about the country's defeat and the hardships of the peace, began attacking relativity as Jewish physics, arguing that it was overly abstract, disconnected from reality, part of a Jewish conspiracy to undermine solid German scientific traditions. These attacks were scientifically absurd but politically dangerous. In 1920, an anti-relativity rally was held in Berlin. Einstein, against the advice of friends, attended and listened to speakers denounce his work. Afterward, he wrote a newspaper article defending his theories, but the vitriol shook him. In 1922, his friend and fellow physicist Walther Rathenau, who served as Germany's foreign minister, was assassinated by right-wing extremists. Einstein was warned that he too might be targeted. He canceled public lectures, kept a lower profile, considered leaving Germany entirely. Yet he continued his work, searching now for an even more ambitious goal: a unified field theory that would combine electromagnetism and gravity into a single framework, demonstrating that all fundamental forces were different aspects of a deeper unity. He would pursue this dream for the rest of his life, never quite succeeding, though the quest itself pushed physics forward in unexpected ways. The quantum debate, Einstein's philosophical stand. While Einstein is rightly celebrated for general relativity, another drama was unfolding in theoretical physics, one where Einstein would play a more controversial role. Quantum mechanics, the physics of the atomic and subatomic world, was developing rapidly in the 1920s. Physicists like Werner Heisenberg, Max Born, and Erwin Schrödinger were formulating new equations that successfully described atomic behavior but seemed to overturn classical ideas of determinism and causality. At the heart of quantum mechanics was uncertainty and probability. You couldn't know both a particle's position and momentum with perfect precision. This wasn't a limitation of measurement, but a fundamental feature of reality. Particles didn't have definite properties until they were measured. They existed in superpositions of multiple states simultaneously. Einstein found this deeply troubling. He had helped birth quantum theory with his 1905 paper on the photoelectric effect. But the direction quantum mechanics had taken, its embrace of fundamental randomness and its suggestion that observation itself affected reality, struck him as philosophically wrong. God does not play dice, Einstein famously objected. He wasn't being religious in any conventional sense. What he meant was that nature, at its deepest level, must be deterministic and observer-independent. There must be some deeper theory underlying quantum mechanics, some hidden variables that, if we knew them, would restore determinism and objectivity. Picture the great debates at physics conferences in the 1920s and early 1930s. Einstein facing off against Niels Bohr, the Danish physicist who championed the new quantum interpretation. They respected each other enormously but disagreed fundamentally about the nature of reality. Einstein would devise thought experiments meant to show inconsistencies in quantum theory. Bohr would carefully refute each one, showing that quantum mechanics, however counterintuitive, remained logically consistent. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics must be incomplete. It described a thought experiment involving two particles that had interacted and then separated. Quantum mechanics predicted that measuring one particle would instantaneously affect the other, no matter how far apart they were, what Einstein dismissively called spooky action at a distance. This EPR paradox, named for the three authors, was meant to demonstrate the absurdity of quantum mechanics. If the theory predicted such instantaneous influences, It must be missing something. Decades later, experiments would show that Einstein was wrong. Nature really does exhibit these spooky correlations. Quantum mechanics was correct even in its most counterintuitive predictions. But Einstein's skepticism wasn't simple stubbornness. He had transformed physics twice by questioning fundamental assumptions everyone else accepted. He believed scientific theories should be beautiful, deterministic, and objective. Quantum mechanics violated his deepest aesthetic and philosophical convictions about how nature should work. In his final years, while most physicists embraced quantum mechanics and moved on, Einstein continued searching for a classical unified field theory, working in increasing isolation from the mainstream of physics. Was this tragic? Or simply the natural arc of genius, revolutionizing science in youth, then becoming, in age, the conservative figure younger revolutionaries must overthrow? Perhaps it's both. Perhaps it's neither. Perhaps Einstein's late career quest, though unsuccessful, embodied something essential to scientific progress. The refusal to accept theories just because they work, the insistence on deeper understanding, the faith that nature's ultimate laws will be beautiful, simple, and comprehensible. The personal man. Music, love, and solitude. Behind the equations and the public fame lived a complex human being, one who found social conventions confining, who struggled with intimate relationships, who sought solace in music and sailing and solitary walks. Einstein married his cousin Elsa in 1919, shortly after his divorce from Mileva. Elsa was warm, practical, willing to manage the domestic and social aspects of Einstein's life so he could focus on physics. But it wasn't a romantic partnership, more a companionship, Elsa serving as buffer between Einstein and the demanding world. He was not, by any measure, an attentive father. His older son, Hans Albert, would later describe their relationship as distant but not unkind. His younger son, Edouard, showed signs of schizophrenia in his teenage years and spent much of his adult life in psychiatric institutions in Switzerland. Einstein supported him financially but visited rarely, finding the situation too painful. These failures of intimacy were real. Einstein himself acknowledged them. "I live in that solitude which is painful in youth," he once wrote, "but delicious in the years of maturity." But where human relationships often disappointed, music never did. Throughout his life, Einstein played his violin, which he called Lena. He particularly loved Mozart's compositions, praising their architectural clarity. Beauty arising from perfect structure, much like a good physical theory. He would organize chamber music evenings, playing with friends and colleagues. Sometimes he'd work on physics problems while playing, his fingers moving through Mozart's sonatas while his mind contemplated the structure of space-time. Picture him on a Sunday afternoon, bow moving across strings, eyes perhaps closed, following melodies that obeyed their own kind of natural law, harmonics and mathematical relationships that produced beauty not through randomness but through structure, through the very determinism he believed must also govern the physical world. He loved sailing too, though he never learned to swim and frequently capsized. There was something about being on water, wind filling the sail, moving according to natural forces, that brought him peace. He would sail alone on Berlin's lakes or, later in America, on a small sailboat he kept near Princeton. His appearance became increasingly disheveled as he aged. The wild hair that became his trademark was partly intentional, a rejection of vanity and social conventions. He stopped wearing socks, claiming they just got holes anyway. He wore the same leather jacket for years, comfortable and familiar. This wasn't eccentricity for its own sake, but a kind of radical simplicity. Stripping away the inessential, focusing only on what mattered. Understanding nature's deepest patterns, standing in solidarity with justice and peace, creating music's mathematical beauty. Exile and America, the final years. By 1932, the political situation in Germany had become untenable. The Nazi Party was rising to power, their anti-Semitic rhetoric becoming ever more violent. Einstein, as a prominent Jewish intellectual, was an obvious target. In December 1932, Einstein and Elsa left Germany for what was supposed to be a brief visit to America. They never returned. Adolf Hitler became chancellor in January 1933, and Einstein's property in Germany was confiscated, his citizenship revoked. He was now a refugee. The Institute for Advanced Study in Princeton, New Jersey, offered him a permanent position, a research position with no duties beyond thinking and writing, surrounded by other brilliant minds, in a country that, for all its flaws, seemed committed to protecting academic freedom. Picture Einstein arriving in Princeton in autumn 1933, a small college town of tree-lined streets and Gothic academic buildings, a world away from the political chaos engulfing Europe. He bought a modest house at 112 Mercer Street, where he would live the rest of his life. His daily routine became famously regular: breakfast, walk to the Institute, work on unified field theory, walk home for lunch, afternoon nap, tea, more work or correspondence, dinner, evening reading or music. Simple, structured, devoted to thought. He became an American citizen in 1940, taking the oath alongside Elsa's daughter Margot and his secretary Helen Dukas. Elsa had died in 1936. He was proud of his American citizenship, grateful for the refuge it represented. But the war in Europe haunted him. Reports of Nazi atrocities, of the systematic murder of Jews across occupied Europe, filled him with horror and helplessness. In 1939, at the urging of physicist Leo Szilard and others, Einstein signed a letter to President Franklin Roosevelt warning that Nazi Germany might be developing an atomic bomb. The letter helped initiate the Manhattan Project, the American effort to develop nuclear weapons first. This was perhaps the most agonizing decision of Einstein's life. He was a lifelong pacifist who had spoken against militarism since World War I. Yet faced with the possibility of Hitler acquiring atomic weapons, he felt he had no choice but to warn the American government. The letter remains controversial. Einstein himself didn't work on the Manhattan Project. The U.S. government considered him a security risk due to his pacifist views, but his earlier work establishing the equivalence of mass and energy provided the theoretical foundation for nuclear weapons. When atomic bombs were dropped on Hiroshima and Nagasaki in August 1945, Einstein was devastated. "Had I known that the Germans would not succeed in producing an atomic bomb," he later said, "I would never have lifted a finger." For the rest of his life, he campaigned for nuclear disarmament and international control of atomic energy. He wrote articles, gave speeches, joined organizations devoted to world peace. Fame, which had brought him little personal satisfaction, could at least be used for causes he believed in. The Sage of Princeton. Final reflections. In Princeton, Einstein became a beloved local figure. Children would stop him on the street to ask for help with homework. Neighbors would see him walking, lost in thought, his hair increasingly white, his face deeply lined but eyes still bright with curiosity. He received countless letters, from students seeking advice, from cranks promoting bizarre theories, from people in trouble hoping a famous scientist might help. He tried to answer as many as he could, responding with patience and often with warmth. A young girl struggling with math wrote to him. He replied, "Do not worry about your difficulties in mathematics. I can assure you mine are still greater." A rabbi asked whether scientists pray. Einstein responded, "Everyone who is seriously engaged in the pursuit of science becomes convinced that the laws of nature manifest the existence of a spirit vastly superior to that of men. This firm belief is a belief in a superior mind that reveals itself in the world of experience, represents my conception of God." He wasn't religious in any conventional sense, didn't believe in a personal God who intervened in human affairs or answered prayers. But he felt a profound sense of awe at the universe's comprehensibility, at the mathematical beauty underlying physical law. This feeling, what he called cosmic religious feeling, was his form of spirituality. In his later years, Einstein increasingly addressed social and political issues. He spoke out for civil rights, corresponding with W.E.B. Du Bois and Paul Robeson, arguing that racism was America's greatest moral failure. When Marian Anderson, the black opera singer, was denied accommodation in a Princeton hotel, Einstein invited her to stay at his home, beginning a friendship that lasted years. He advocated for socialist economic policies, believing that capitalism inherently created inequality and valued profit over human welfare. This made him suspect during the McCarthy era. The FBI maintained a massive file on him, considering him a possible subversive. Einstein faced these attacks with the same calm he brought to scientific criticism. He had long ago stopped caring what authorities thought. Truth and justice mattered. Reputation and social standing did not. The final equation. In April 1955, Einstein's health began to fail. An abdominal aortic aneurysm that had been monitored for years began to rupture. He was hospitalized at Princeton Hospital. Doctors suggested surgery. Einstein declined. "I want to go when I want," he told them. "It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." Imagine him in that hospital room, 76 years old, knowing death was near. He asked for the pages he'd been working on, still trying to complete his unified field theory, still searching for that final elegant equation that would tie everything together. On April 17th, he worked on his equations. On April 18th, he died peacefully in his sleep. He left instructions for his brain to be studied. It was, though controversially, and showed no obvious anatomical basis for his genius, and his body to be cremated, the ashes scattered in an undisclosed location. No grave, no monument, no place for pilgrimage. He wanted to be remembered for his ideas, not worshipped as an icon. The universe still hums his song. And so we return to where we began. That quiet room, that lamplit desk, that mind gazing at the stars and wondering, what was genius? What made Albert Einstein able to see what others couldn't? Perhaps it was the way he never stopped asking childlike questions. What would it be like to ride alongside a beam of light? Why does a compass needle point north? What if there is no such thing as simultaneous events? Perhaps it was his ability to trust his intuitions even when they contradicted common sense. His willingness to embrace paradox if logic demanded it. Perhaps it was his philosophical conviction that nature, at its deepest level, must be simple and beautiful, that complexity is a sign we haven't yet understood things properly. Or perhaps, and this feels closest to truth, it was simply an unstoppable curiosity combined with the courage to follow ideas wherever they led, regardless of whether they made him comfortable, popular, or confirmed in his beliefs. Einstein transformed our understanding of space, time, gravity, and energy. But more than specific theories, he left us a way of thinking. Questioning assumptions, seeking deeper patterns, trusting that the universe is comprehensible, that with patience and thought we can glimpse the elegant structures underlying apparent chaos. General relativity continues to be confirmed with remarkable precision. GPS satellites must account for relativistic time dilation. Gravitational waves, ripples in space-time predicted by Einstein's equations, were finally detected in 2015, a century after he first predicted them. Black holes, those regions where space-time curves so extremely that nothing escapes, are now routinely observed. E=mc² powers the sun and stars, explains how elements are forged in cosmic furnaces, enables both medical treatments and terrible weapons. And quantum mechanics, despite Einstein's objections, has proven spectacularly successful, underlying all modern electronics, revealing a universe stranger and more wonderful than even Einstein was willing to accept. He was right about some things, wrong about others, but his wrongness was itself productive. His objections to quantum mechanics forced its defenders to think more clearly, to address deep philosophical questions, to conduct experiments that revealed ever more about nature's fundamental strangeness. This too is genius. Not being always right, but asking questions so profound that even the wrong answers advance understanding. Drift toward the stars. As you settle deeper into rest tonight, dear listener, imagine yourself back in that patent office in Bern, early 1900s. The alpine light slanting through windows. A young man at his desk, unknown to the world, working quietly on problems that would reshape human knowledge. No fanfare, no expectation of fame, just pure curiosity, the joy of understanding, the pleasure of watching patterns emerge from chaos. Imagine the universe as Einstein came to see it. Not a clockwork mechanism of particles moving through empty space, but a dynamic fabric, curved and flowing, where matter and energy and space and time dance together in mathematical harmony. Imagine starlight bending as it passes near the sun, following the curves in space-time the way a marble rolls along a curved surface. Not because the sun pulls it, but because space-time itself is curved, and light simply follows the straightest path through this curved geometry. Imagine time running slower near massive objects, faster far from gravity's embrace. Every atom a compact bundle of frozen energy, E equals mc squared, waiting. The universe expanding, space itself stretching, carrying distant galaxies away from each other not by moving through space but by the expansion of space itself. All of this Einstein saw or predicted from that quiet study, from those patient calculations, from his willingness to trust mathematics and logic even when they led to conclusions that seemed impossible. And the music, don't forget the music. Mozart's sonatas playing while his mind traced geodesics through curved spacetime. The violin's voice rising, pure and mathematical, beauty emerging from structure, from pattern, from the same deep principles that govern falling apples and orbiting planets and the gentle bending of starlight. What was he seeking, this gentle man with unruly hair, this dreamer who transformed physics? Perhaps the same thing we all seek when we look up at the stars, to understand our place in this vast, mysterious, beautiful universe. To see the patterns that connect us to the cosmos. To know that we, too, are part of the dance. Stardust conscious of itself, the universe contemplating the universe. Einstein once said, "The most beautiful experience we can have is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science." He never lost his sense of mystery. Even as he unveiled the mathematics governing gravity and light, he remained in awe of existence itself. Why is there something rather than nothing? Why is the universe comprehensible? Why do mathematical equations, abstract human inventions, describe physical reality with such uncanny precision? These questions, he knew, lay beyond physics. They touched on philosophy, on meaning, on the fundamental wonder that makes us human. And so he continued wondering, continued seeking, continued asking why. Like a child who never grew out of that most beautiful phase, when the world is new and strange and everything calls out for understanding. The lullaby of gravity. As sleep draws near, let your mind settle on this. Somewhere above you, even now, space and time are curved by Earth's mass. You lie in a gentle dimple in space-time, held by the planet's gravitational embrace. Not pulled down by a force, but simply following the natural contours of reality. The path of least resistance through curved geometry. The moon traces its monthly orbit through a deeper curve created by Earth. Earth orbits through the sun's deeper curve still. The sun moves through curves created by the galaxy's billion stars. And all of it, every planet, every star, every grain of dust, warps the fabric of space-time around it, creating an impossibly complex, constantly shifting geometry that somehow balances into beauty. This is the universe Einstein revealed. Not dead matter following rigid laws, but a living geometry, space and time breathing together, matter and energy interchanging. Everything connected through the mathematical harmonies he learned to read. And it hums, this universe. Listen in your imagination. The deep bass note of massive stars curving space-time dramatically. The middle tones of planets tracing orbital rhythms. The high harmonics of light waves rippling through electromagnetic fields. All of it combining into a cosmic symphony, playing eternally, whether we listen or not. Einstein heard it. He transcribed parts of it into mathematics. He tried to show us what he heard, to teach us to listen. And now, as you drift toward sleep, you carry his gift. The knowledge that you live not in empty space with time ticking uniformly everywhere, but in space-time, a unified fabric curved by every bit of matter, where time flows at different rates depending on gravity's strength, where nothing is quite what it seems but everything is connected. You are not separate from the universe. You are space-time contemplating itself. You are atoms forged in ancient stars, arranged into patterns complex enough to wonder about the stars that made you. Einstein, that patent clerk turned sage, that violinist who spoke with mathematics, spent his life trying to read the score of this cosmic music. He succeeded partly, failed partly, but never stopped listening, never stopped wondering. As you fall towards sleep, you are falling freely, weightless in Einstein's sense, following your natural geodesic through curved space-time. No force acts on you in this moment. You are simply being, existing, moving along the straightest path through the geometry of reality. Tomorrow, when you wake, perhaps you'll look at the world a little differently. Perhaps you'll remember that time is relative, that space is curved, that light takes time to travel, that the sun you see is the sun as it was 8 minutes ago, that you live always slightly in the past of distant stars. Perhaps you'll remember that a curious child who spoke late and questioned everything grew up to reshape human understanding. That genius isn't magic but patience, persistence, courage, and wonder maintained across a lifetime. Perhaps you'll remember that the most important thing isn't having all the answers but continuing to ask beautiful questions. Gentle farewell. Thank you for spending this quiet time with us tonight, exploring the life and mind of Albert Einstein. I hope his story brings you peace as you prepare for rest. The peace of knowing that we live in a comprehensible universe, beautiful in its deep structure, waiting patiently for curious minds to unveil its secrets. If these gentle journeys through history and science help you unwind, if you find comfort in knowing you're part of a community of curious souls seeking wonder before sleep, consider subscribing to The Sleepy Scholar. Your support, a simple subscription, a like, a quiet comment, helps us continue crafting these bedtime explorations for thoughtful people like you. But no pressure, no urgency. Simply know that you're always welcome here. Any night you need a calm voice and a story to carry you toward dreams. Sleep well, dear listener. May your dreams be filled with starlight bending gracefully through curved space-time, with equations blooming like flowers in spring, with the gentle hum of the universe singing its eternal lullaby. Until we meet again, good night from the Sleepy Scholar. The stars are still there, waiting. The universe still curves and flows and dances according to patterns Einstein helped us see. And somewhere in the mathematics describing gravity's gentle pull, perhaps his spirit lingers still, wondering, questioning, forever amazed at the mysterious beauty of existence. Rest now. Let the universe hold you in its gravitational embrace. Follow your geodesic toward morning. Good night.